This is Deepak Singh from Entity Solutions, and in this video we are going to talk about remote field testing. As all of you know, this is one of the two testing method. There are many methods like eddy current testing, remote field testing, and then MFL, then NFT, then IRIS, and RFET is one of them. And all the techniques have their own benefits and applications. So accordingly, RFET having also the same. And in this all video, we are going to discuss how this RFET going to help us in the field of inspection, tubular inspection. So many people get confused about RFT, RFET, or what is remote field eddy current testing. Actually, all are same. Just few people call it RFT, and few people call it RFET, and few people call it RFEC. So RFET means remote field electromagnetic testing. RFT means remote field testing. RFEC means remote field eddy current. So all are same basically. It's just to say many in different part of the world people call it different way. So basically, why we need remote field testing, and there are already many methods like ECT, MFL, NFT. There are many methods for tubular inspection. Then why we need remote field testing? Basically, in eddy current testing is used for the non-ferrous material inspection, where the primary field eddy current works well. But when we are going to inspect the ferromagnetic material like carbon steel, that is there is a challenge where we cannot use eddy current. Then this remote field testing comes into the picture. Why there is a challenge? Because in carbon steel, that permeability of carbon steel is too high comparative to ferromagnetic, non-ferromagnetic material like SS316 or 304 or copper nickel. So in that case, permeability is around 1, we can say. But in carbon steel, it varies 500, more than 500, even sometimes it goes 1000 also. And it is not even throughout the tube or throughout the material, it is not even. So the behavior of electromagnet or eddy current is not same throughout the length. So that's why we cannot use eddy current. So we need something new which can help us to inspect the carbon steel tube or ferromagnetic tube. So this remote field testing comes into the picture. This is not something new. It has the existence since 1970, and now ASME and ASMT also recognized this thing as a tubular inspection technique in ET. ET is a method and RFT is a technique now. So it is recognized by ASTM and ASME also. So RFT is a electromagnetic technique that utilizes an AC exciter source. The uh, the this electromagnetic energy travels along the tube wall for some distance in both directions from the exciter coil. The distribution of the primary field is dependent upon the magnetic properties of the tube wall thickness, and the presence of surrounding tube structure. These things already you have many resources to go through it. There are standards in SME section 5 also, in article 17 you can go through it. You can have the literature in volume 17, and you can refer SME STME 2096. All those things will be there. Why we are using, on what dia, on what thickness we can use it. Basically, in this video, we are going to tell you the main operation, what technician don't do at the time of inspection, and what the things they has to keep in the mind before before inspection. So all those things they missed it, and RFET is not a very simple part which everybody can do, but it can be simpler when we follow the procedure or when we follow the instructions. So it will help in the precise and accurate inspection. Apart from that, all these things we can go through it. You can take a snapshot or you can pause the video and you can read it. And this is nothing new which I am going to tell you. Uh, this is already available all over in the Google, so you can Google it and you can go through it. Even if you don't if you don't have the time, then pause the video and go through it. So this picture represents what is remote field testing. Why we call it remote field testing. So this picture will tell you why we call it as a remote field testing. We can see here in this chart there are three lines which represents direct field, indirect field and resultant field. Resultant field represented by green, indirect field represented by orange and direct field represented by the red line. So what happened, and you can see the probe also here below. So in this probe there is one exciter and one receiver. One coil is exciter and one coil is receiver. When exciter generates a magnetic field, it generates a eddy current nearby, and that is our here. That is our direct current. And as you know, the carbon steel having permeability very high, so that resultant magnetic field or secondary magnetic field is also very high. That in that case, that magnetic field is not homogeneous in this range, or you can say till here this is not homogeneous, or it is very high, it is very, the secondary magnetic field is very dominant, so we cannot use it for the inspection. Later on, if we go a little bit further, this is our transition zone. This is called transition zone. We can see here, this is called transition zone. So till here to here there is a transition zone where we where again there that all the three magnetic fields are getting intersect. So that magnetic field again, there is no homogeneity and we cannot trace it, we cannot follow similar path. So again this reason again we cannot use it for the inspection. But later, after approx 2D of the tube, 2 OD means 2 times of the OD away from the exciter, we have the common interest. We have a resultant field in a homogeneous way, so that we can use it for the inspection. Maybe the next slide will help you to understand better. It's a finite element method where we can see the behavior of electromagnetic field in the tube. We can say this is our tube, here is our exciter, and all these are your magnetic field. All these are your magnetic field. We can say till here this is our exciter, and till here this is our direct zone where density of the electromagnetic field is too high. Secondary magnetic field again there is too high because of the high permeability of the carbon steel. It is approx 500, more than 500, and it varies on time to time or place to place. Again here we can see after this region, this one is your transition zone, or if you want to see the transition zone, here it is elaborated expanded way. So again there is no homogeneity and we cannot use this magnetic field, this region magnetic field for the inspection. But later on after this region, you can see the magnetic field are almost almost parallel to the tube, or almost parallel to the axis of the tube. So this field can be used for the further inspection. When there is a leakage or due to any kind of discontinuity, there is a defect or there is a permeability change, this will give you the value in the term of phase and amplitude, which can be used for the further analysis. So In RFET, basically we are using three kinds of probes are available. First is single exciter, then dual exciter, then dual pickup probes. There are differences and there are applications also where and why we can use all these where we can use these three probes. Basically, mainly single exciter and dual exciter probes are has been used all over the world. So single exciter can be used for general purpose probe for wall detection, wall loss detection, clear response on wall loss and erosion defect. Two channel absolute and differential are active here. Probe is optimized for absolute analysis. In this single exciter probe, absolute are dominant, but for differential or small flaws, it is very difficult to detect. Like here it is mentioned, differential channel is blind to detect on the near side of the support plate. We can get it, but very hard to find. But it is not same for the dual exciter. In dual exciter, we can get the small defects also used when fittings is expected in the tubes. Two drivers switchable lead both trial. Two channel both absolute and differential. Probe is optimized for the simple differential interpretation. Clear response on clear response to small defect. As I told you before, it has been used for the small kind of fittings. We can use it if we are expecting small fittings in the exchanger or in the tube, so we can use dual exciter. Or if there is a gradual wall loss, if we are expecting gradual wall loss or erosion kind of things, then single drives is okay. But if we are suspecting fittings, so we can use dual exciter probe. Similarly, there is a probe by dual pickup probe. It is almost work for both. We are what we are getting in single exciter and what we are getting in dual exciter. This probe works for both of it. Used when defects are expected at the tube sheet location. Four channels are available. Continue advantage for both single and dual drive mode. Both data analysis is longer and require experienced user, because the for a single, why this line is here, because single defect may generate multiple indications. So that's why we need to very sure which indication is your actual one, because in this one, two, three, four, five indication you will get for a single defect. Like this indication you may get for a single defect, but it is not here. We can compare here. Let's go for the, and what happened with dual driver. Dual driver we will get like this indication. This is for the two dual driver and this is for the receiver. And how we get the indication in single drive, we'll get the indication like this. You'll get the indication like this here. So hope you, if you had experienced for single drive and dual drive, you may correlate these indications with that, and you can find how it works. So in this slide, we will see how this vertical strip chart and how what this vertical strip chart represents. So we are when we are using that software, we are having two types of representation: strip chart and this Lysagius chart. In strip chart, we will get the indication like this, and whenever we select any particular point, that indication will represent in the Lysagius one. So for vertical, if we click on the vertical channel, so vertical channel means this represents this value here. This is the, or we can measure it as a phase or voltage, whatever it is. This will represent this value, vertical value. and if you are clicking on the horizontal one, so this horizontal one is this one. The voltage will show here how much voltage it will represent like this one. Similarly, in RF, if you are talking about RFET, so we cannot leave this image. This is so-called your voltage plane. In voltage plane, this is everyone know this thing. So in this is not very simple. We need to understand what all these represents. So we know this is our baffle plate or support plate, we can say. So this point is our nominal tube thickness, and this is our infinite thickness. Infinite is, it doesn't mean it having infinite thickness. Infinite in the term of your tube thickness. Let's say tube thickness is 2.1 or 2.3. So in that term, this thickness is very high, so we call it as a infinite thickness. And all these spiral, logarithmic spiral, so this represents the volume of the defect, we can say, or the degree of the defect. If any defect crosses this line, so it means that is having 360 degree defect, like here it is mentioned. So defect is circumferential and almost 360 degree, and if any signal crosses this line, it means it is having the potential of 270 degree or nearby angle in the tube. Similarly, here for this line, if some indication crosses this line, so this means it is having 180 degree, and if it is crossing this line, it means it is 90 degree. So accordingly we can say that volume of the defect how it is. So hope it is clear for everybody. So this is, again I am repeating, this is our nominal thickness point, and this is infinite thickness point. This is your spiral logarithmic spiral indicator. So this represents 360 degree defect, this represents 270 degree defect, this represents 270 degree, sorry 180, and this represents 90 degree. If you have the calibration tube, again try it, and if there is a 360 degree, it will cross this line 100%. And if you have 270 degree or tapered flaw, it will cross this one, and if you have 180 degree, it will cross this one. And if you have like holes, through hole, or this 80% or 60% flat bottom hole, it won't cross this one also. It will be like this. The indication will be like this. It won't cross this line. So try this and let me know. So in any inspection, whether it is eddy current or RFET, the frequency selection is very important, and we can, and all the defect sensitivity depends on the frequency, whether we can get it or not, or how we are sizing it. So all depends on the frequency, on what frequency we are acquiring. So both positive and negatives are there when we are using higher frequency and lower frequency. It is same as ECT and or UT or whatever you say. If you are using high frequency, it means better precising and depth sizing, and if you are using low frequency, it means the phase separation will be low, and defect catching power, you can say, it will be high, but sizing will be the difficult. Sizing will be difficult if you are using low frequency. So we need to compensate it, or we need to compromise for the both. We need better precision also, and we need better detection also. So we should select such frequency which will help us to detect the defect also and to size the defect also. So this no need to any formula you need to apply. If you had used MS5800 or multi-view or Actin equipment, so whenever we start making the wizard setup, so what we do generally, what we do, we just give the value of the thickness and the material, so that equipment suggests itself that optimized frequency. On that frequency, what we do, uh, we just calibrate our calibration tube and start doing the inspection. But that is not true. We need to check that suggested frequency by the equipment is correct or not. Then how we can assure that suggested frequency by the equipment is okay for the inspection or not. So there are basically two techniques to check the frequency whether it is okay for the inspection or not. First technique, here it is said, if we have two consecutive defect like 20% or 40% or 40 or 60, then the phase separation between both should be 15 to 20 degree. The phase separation between that is 15 to 20 degree. Here we can say in absolute channel the phase separation is 17, and in differential channel the phase separation is 18 degree. So if it is in that range 50 to 20, then our frequency is okay for the inspection. Then what's the second technique say? Let us say we have the flat bottom holes 20 degree, 40 degree, 60, 20%, 40%, 60%, and of course we have a hole, through hole. So what we have to do, we need to pull the data, and we need to rotate the hole at 90 degree, and again then we have to check the phase of 20% flat bottom hole. It should be, when we keep our hole at 90 degree, then our flat bottom hole 20% should be at 150 degree, in the range of 150 degree, 150 to 155. So if it is there, then we have the centralized frequency where we can use it. What if it is not there, either in the first technique or in this second technique? What this phase separation is here only, the 120 or something is there. Then what we have to do, if the phase separation between hole or flat bottom through hole and 20% flat bottom hole, then what we have to do, we have to increase the frequency. This is very common technique. I think we all know this thing. We need to increase the frequency. If that phase separation is higher, then what we have to do, we need to decrease the frequency to keep it in the range. So most of the technician or most of us, we don't do this practice, but we need to do it, and try to do further. If we are going to new inspection, try this one. Don't try, this is the very essential part of the inspection and making the setup and making calibrating the system. This is the very essential part. We should not miss it. Okay. Apart from that, there are one more crucial part of the calibration or making the setup. We don't see on what bandwidth we are using, on what bandwidth we are inspecting the we are doing the inspection. Let us say if we are using 60 Hz power supply, then here is the band strip chart which we need to follow. The blue lines are showing the allowable frequency, and the red lines are showing not allowable frequency. Let us suppose we had given, and our center frequency comes in the range of this after 365 Hz. So what should be our bandwidth? Our bandwidth should be 25 Hz, and our pulling speed should be 0.3 meter per second. Accordingly, if our frequency comes in between 310 to 380, 355, then our bandwidth should be 15 Hz, and our pulling speed should be 0.22 meter per second. So these we have to follow. But what if our center frequency comes in this range? Let's say in 290 to 310. What we have to do? Either we have to come in this range, we need to set our frequency in this range or in this range. Keep in the mind that phase separation between for the frequency selection follow the same. And again, if you are using 50 kilohertz power supply, then again the rule is same. We need to select the frequency according to this bandwidth. It is available for both the equipment, whether we are using 85 or we are using this one MS5800. In their manual it is already there, and I think we need to keep it with us while doing the inspection, or if you don't have, just take the printout and stick it in the inner side of the box. So whenever we are making the setup, so this stick chart is in front of us, so while selecting the frequency we can give the proper bandwidth also. Now in RFET, very important term, you people have heard about it, but nobody does. Frequency compensation. If somebody is doing RFET, I cannot digest कि they haven't heard about this term frequency compensation. What is frequency compensation and why we need it? So further we are going to discuss this thing. Why we need frequency compensation, that we will come to later. But whenever we are going to inspect carbon steel tube, there are a lot of problems which we may face. Like each rows of the tube may not behave like same. Like first row, that baffle support signals behave in different way, or in between the bundle it will behave in different way, and at the end, whether if we compare the inlet tubes and outlet tubes, it will behave differently, all because of the change in the permeability, change in the thickness value, or and maybe defect near to the baffle plates. All depends, all are the factors which may vary your baffle plate signal that appears. So so this slide represents how this baffle plate will be appear on your screen when we are using single drive. If you are using a single drive probe, so your baffle plate will appear like this, and the angle for that one is 180 to 230 degree. But at the same time, if you are using dual drive probe, your signal will appear like this, and the angle for that one is 0 to 50 degree. 0 to 50 degree, actually in dual drive that signal will reverse, and that's why it is 0 to 50, and here it is 180 to 230 degree. Similarly, in differential channel, we'll get the support plate in 215 degree, and for the same, if you are using dual drive, we will get it approx 33 degree. It may differ also, depends upon the material and depends upon the thickness, but not much. So keep in this mind, many times we get confused why our baffle signal is coming like this and why we are getting like this. If we are using single drive, our baffle plate support plate signal appears like this, and if we are using single dual drive, so our baffle plate will appear like this. Now, how this baffle support plate signal differ? In We all know, while manufacturing the tube, there is a tolerance of plus minus 10% in their thickness. That thickness may vary 60 degree your support plate thickness, support plate orientation. If let's say if something is some tube is 2.1, so you had arranged your baffle plate signal like this in a horizontal plane, and if it became 2.2, it may vary like this. Your baffle plate signal will vary. It may vary up to 60 degree. At the same time, if there is a variation in the property of the material, like I said, if there is a exchanger, like there is in inlet and outlet. In inlet, maybe hot material is going, and another in outlet the cold material is going out. So in this way, that it may vary the permeability of the tubes, or exterior tubes, periphery tubes of the bundle may have the different property rather than the interior tubes. Or there another case can be like if some tubes got damaged, so there is a requirement of retubing. So that retubing may not of the same heat number, so that property of that particular tube is differ from the other tubes, so that may also affect your support plate signal. And apart from that, defect at the support plate, if there is a defect or nearby the there is a defect under the support plate or nearby the support plate, that may also change the angle of the support plate. And another thing is bundle effect. Have you heard about this one, bundle effect? What is bundle effect? Bundle effect is nothing, just a effect of nearby tubes while doing the inspection. If we pull the data from the periphery of the tubes or first row of the tubes, it will behave different rather comparative to the data of in between the bundle. Why? Because that exterior tubes are not surrounded by the many tubes, and the in between tubes it is surrounded by the many tubes, which may that electromagnetic field, it is going throughout the wall thickness, and it may vary by, or it may get influenced by other tubes. So that is called bundle effect, and that may change your orientation, support plate orientation. So, so all these orientation, all the tubes have different orientation. How we can rectify this? And we cannot we cannot make a setup for periphery. We cannot make another setup for inlet, and we cannot make another setup for outlet or different portion. So we need something which can, on what frequency we can do all the inspection. We need to select some better frequency where it compensates all these kind of variation in the range. So there are that is called frequency compensation. We are compensating our frequency to keep all these variables in some particular range. So there it can be of two types. So first one is frequency compensation, and second one is realignment. So frequency compensation is the recommended one basically, and we has to try this frequency compensation when the support plate signal orientation is beyond 30 to 45 degree. Like uh, okay, so our first baffle is coming in this range, and second at another tube it is coming in this range. If this is 30 degree, if the variation is 30 degree, then we no need to do the frequency compensation. But if it is beyond 30 to 45 degree, then we need to do frequency compensation. If this can vary anyway, here or in any direction. So if this angle separation is greater than 30 to 45 degree 45 degree, then we need to do that frequency compensation. And if the another one is realignment, this that analyst has to do this one. If that variation is in between 30 degree, some tubes is coming like this, some tube is coming like this, some tube is coming like this variation is, if 30 degree, then at the time of analysis we need to balance it and keep it in the keep it horizontal, then we need to analyze the defect. So we are not going to discuss this realignment. This is very common, and every analyzer has to do before analysis. And this frequency compensation very few people does, and how it can be done, now we are going to discuss this one. So this is a representation what we has to do if our support plate lies in this range. So if our support plate lies in this range, what we have to do, we need to increase the frequency. to bring it in this direction. If our support plate coming in this direction, so what we have to do? We have to decrease the frequency to bring our support plate horizontal at this position. If our support plate varies in this region, so realignment can be done. But if our support plate coming in this region or in this region, we need to increase or decrease the frequency based on the orientation of the support plate. So this picture also represents the same what we had discussed in last one. If your support plate lies here, so we need to increase the frequency, sorry, decrease the frequency. And if your support plate is coming in this direction, so we need to increase the frequency to bring it down. So we cannot make it all in zero position. We cannot bring all the baffle plate in the zero position. But we can do this, we can try to bring it in the realignment zone. Realignment zone means that variation in any of the bundles should be 30 to 45 degree. If it is there, then our frequency is okay, and if it is not there, we need to do this practice. If it is done, then again what we have to do, we need to rescan the tube, and we need to check randomly on all over the bundle, on the periphery or in the between and the calibration tube. So if that range is coming in the realignment zone or 30 degree variation, 30 to 45 degree, then our frequency is okay now for the inspection. So what next we can do? We can save the setup, and with a new name or whatever the exchanger name is there, you can give it that name, and we need to pull the data on that frequency. So this is very important thing, frequency compensation. Particularly the purpose of this video was that one only. And whenever I was making this video, so I thought a little bit details also I should give, what is probe and why it is what are the necessary things need to discuss about the probe, why we are using single, why we are using double, and what are the benefits, that also I should cover. So that's why I try to give you the inputs, and there are many more things which I cannot which I cannot elaborate here. And mainly all the materials are available, so only thing is we need to go through it and we need to read it. So all here we have given the reference from where I took this all, and you can also go through it. STM E2096 volume 17 SME section 5, actually article 17 also, that particularly for the RFET. And whichever equipment you are using, if you are using Olympus, then go through the manual. In that manual it is very clearly mentioned that how to make the setup, and what is the how to do the frequency compensation and everything. For the same, we can use the Edify manual if you are using Edify equipment or Actin 1 or Actin 2. So basically we need to go through it. Nobody follow this manual, but for good inspection or precise inspection, we need to follow the instructions what they had given. So thank you guys, and I hope this video help you in future. And if apart from that, if you need anything else, or in the same video, if you need if it is something is not clear, you can write in the comment box, so we can make a separate video, or I will try to answer you there. And if you want to contact on this number, or you can mail it on this mail ID. So we are always ready to help 24 into 7. For any particular kind of training, particularly for the tubular inspection, you can contact on these numbers. Thank you guys.